It's my pleasure to introduce Thomas Koberda of Harvard University, who will speak to us today about residual properties of three manifold groups.
Thank you very much for the invitation. So throughout this talk, we're going to be considering M, which is going to be a compact three-manifold. And we want to understand the algebraic structure of pi1 of M. And one way to understand some of the algebraic structures to understand what sorts of quotients pi1 admits. So we say that a group G is residually K, where K is some class of groups if for each non-identity element G, there exists a homomorphism from G to a group F, which is an element of this class K, such that G is not in the kernel of phi sub G. And the main classes of groups that we're going to be considering, these are going to be P groups and torsion-free nilpotent groups. And so we're going to try and understand some three-manifold groups, which are going to be what we call residually P, or residually torsion-free nilpotent, or more generally, virtually residually P, or residually torsion-free nilpotent. Whereby virtually we mean after passing to a finite index subgroup, equivalently a finite cover. So the first reductions that we're going to make the first assumption we're going to make is that M is orientable, which we can always assume after passing to a finite cover. We're going to assume that M is irreducible. So that means that M doesn't decompose as a non-trivial connect sum. And then after we then we start out with M is going to be a compact irreducible three-manifold. We're going to assume that its Euler characteristic is equal to 0. And then we apply the geometrization theorem, which implies that M can be decomposed as a union over tori of these pieces M sub I, and each M sub I admits one of 8 geometric structures. So most of the details of this talk will concern these actual pieces M sub I that we get by cutting up M. So we're going to call these pieces geometric. And so the geometrization theorem tells us that M sub I is going to fit into one of 8 categories. So those geometries are S3, S2 cross R, R3, H2 cross R, nil, Solv PSL2 R tilde, and H3. And now if we have a manifold M sub I, which admits one of these 8 geometric structures, then we can ask, is it going to be virtually residually P or virtually residually torsion-free nilpotent? And we can summarize the main results in a little table. So manifolds admitting S3 geometry have finite fundamental groups. So both of these are vacuous. S2 cross R geometry admits a virtually cyclic fundamental group, so both of these are true. Euclidean geometry is virtually torsion-free abelian, so both of these hold. H2 cross R is virtually surface group cross Z, so again, both of these hold. Nil geometry is virtually torsion-free nilpotent, so both of these hold. Solv geometry is the first instance in which we get something interesting. So we do have virtually residually P for every prime, and we never get virtually torsion-free nilpotent. PSL2R geometry, we get virtually torsion-free nilpotent, and so we get virtually residually P. And for H3 geometry, we again have something interesting going on, that we have virtually residually P, and we don't know about virtually residually torsion-free nilpotent. And the conjecture is that yes. So let me.
Conjectures, yes, a whole bunch of people.
Yeah, so this. So I'll make some remarks as to this conjecture in just a little bit.
Let's understand the structure of the product. How are you going to reduce to the reducible case? You're going to show that, or is it easy?
So in the why can we assume that so if the manifold itself is reducible, then the fundamental group is a free product,
Right.
And so then if we have a free product of two groups which are virtually residually P, then the free product is virtually residually P. And if it's a virtually residually torsion-free nilpotent, then I'm actually not very sure about that. So that's why I want to concentrate on the actual geometric.
So the reduction is conjectural for the second category.
Yes.
Here for the first one.
Yes.
Okay.
I mean, it's not completely obvious why it's clear in the first category, but it follows from Bass-Serre theory, for instance, or the Courrosh subgroup theorem. So we might make some remarks. First, about the connection between residually P and residually torsion-free nilpotent groups. Actually, first let me talk about this conjecture here about hyperbolic 3 manifolds. But what is known is that so if M is a hyperbolic 3 manifold, which we assume is closed, then a recent result of Kahn and Markovich shows that there exists an immersed surface sigma, which is immersed closed surface sigma sitting inside of M. one very large conjecture at the moment.
Is what is power injected? Or?
Yes, I'm sorry. Immersed, closed, incompressible. Thank you. There's a conjecture now that such a surface subgroup, G, sitting inside of gamma, is separable. And if this were true, then this would imply the virtually Hawking conjecture.
So maybe I'll explain what separable means. It's a generalization of residually finite.
Yes, so separable meaning that G would be equal to the intersection of all subgroups K of gamma, which contain G and have finite index.
So who is separable, G or the map G to gamma?
So I'm identifying G with a subgroup of gamma. So
Oh, I see. Okay. And then it's separable if
if it's the intersection of all finite index subgroups containing it.
so if the theorem group is separable, then the group is
Residually finite. That's correct. So if one could show this, then any immersed incompressible surface the image of whose fundamental group was G would actually lift into an embedded surface on a finite cover.
Okay, maybe write down this statement. I didn't quite understand.
Yes. So the precise statement is that if you have K a finite CW complex, and you have a map from K to some other CW complex X, and you assume this is pi1 injective, and call this map phi, we assume that phi of K is immersed. And we'll also assume that that the image, so phi of pi1 of K, is separable in pi1 of X. This implies that there exists a finite cover X prime sitting over X, so that this map phi factors and this phi prime is an embedding. So this is a conjecture at the moment.
So the conjecture is that in every subgroup of a hyperbolic manifold group is separable.
So that seems less likely to be true, but the hope is that every surface subgroup is separable.
I see. So I'm still trying to see the statement. So statement 2 is what? G is what?
G is pi1 of the surface.
Oh, I see. So this is a conjecture, right?
Yes.
G for sigma is sigma, any sigma or sigma compressible?
It's so. I mean, what?
So not injective, right?
Yes. So once we have this surface subgroup, and this is represented by a map from a surface, which is generically going to be an inversion.
So the conjecture is if, understand, if every G is separable, then you have this conjecture? Or the
Yes.
Okay.
Yeah. Because we know that we can always find such a surface group, and the hope is that every surface group is separable, and if that is true, then there's an embedded surface in a finite cover.
And that's the virtual Hagen conjecture?
Yes. And now, recent work of Danny Wise has shown that if M is H3 mod gamma and M is Haken, then this implies that M is virtually fibered. In the sense that it fibers over the circle. And this in particular implies that gamma is arithmetic or M virtually fibers. There is another even stronger conjecture than this, which says that if gamma is the fundamental group of any hyperbolic of some hyperbolic 3 manifold, then gamma virtually injects into a right-angled Artin group. And if this were true, then we would know the answer to this question, and the answer would be yes. And
So 3 is a theorem, 4 is a conjecture.
correct. So in some sense, 1 is weaker than 2, and 4 is stronger than both 2 and 1, and 3 is something in between that says if we knew that if we knew that 1 implies 2, then we would know immediately that 1 implies 3.
So can you maybe make that diagram 1, 2, 3, 4 vertices of that tetrahedron and some arrows?
Sure.
But without the raising the theory.
So this is just about the separability.
Okay.
I'd have to, I can yank one of the whiteboards off of one of the walls and then the rooms bring it in. There's only so much space.
So
Summarize this.
we have 1, 2, 3, and 4.
Okay.
So 2 implies 1, 4 implies 2, and now
And then 1 implies 2 implies 1 implies 3. Sorry, 1 implies 4.
3 says 2 implies 4. 2 implies, no, it doesn't quite imply 4. 2 implies the virtually fibered conjecture.
And which one is the theorem? 3.
3 is a theorem, and 1 is also a theorem.
But I wasn't joking. At some point, didn't you say if we knew that 1 implied 2, then we would immediately know that?
Oh, no, so if we knew that 2 was true, which would imply that which would be if we can find such a surface group, then it's immediately Haken on a. Then we would know that the virtually fibered conjecture holds.
And does 4 would imply that gamma is a reefer?
Yes, that's exactly the idea.
The gamma is what?
You're going to explain that?
Did you say reefer?
Yeah.
Refers, yes. So
That's if we're taking you too far off.
I can say this one pretty quickly. So we say that a group is reefers, which stands for residually finite, rationally solvable. If G admits of exhausting filtration of finite index subgroups, so the intersection of the GIs should be the identity, and also it's known that and so one would have to also that's the residually finite piece, and the rationally solvable piece says that the kernel of the map GI to GI ab tensor Q. This has to be contained in Gi plus 1. So Agel says that if G equals pi 1 of M, and the Euler characteristic of M is 0, then G virtually fibrous.
If G is refers.
Yes. So
Yes.
G refers. Then M virtually fibrous. I'm sorry.
But then there is a further theorem that if it embeds in the rag, then it's
So then right-angled Artin groups are all refers, and a subgroup of a group which is refers is also refers.
Okay, so then 4 plus Agel implies
Implies
everything.
implies everything. Okay. So allow me to also make a remark concerning the relation between groups which are residually P and residually torsion-free nilpotent. So if G is finitely generated, then the following are equivalent. One is that G is residually torsion-free nilpotent. Next is that G is residually finite P for all primes and has a certain technical property U, which I will explain in just a second. And the third is that G is residually P for infinitely many primes and has property U with respect to that set of primes. So what property U says, if we have a non-identity element in G, then there exists an M sub G, which is independent of either here the set of all primes or the set of these infinitely many primes, such that G is non-trivial in a P group quotient, which is less than M sub G step nilpotent. So the reason this is true is a little circle of ideas. One implies two follows from the work of Maltze, which shows that every torsion-free nilpotent group can be embedded as a lattice inside of a finite-dimensional real Lie group. 2 implies 3 is trivial. And then 3 implies 1. 1 takes an element G in G and then finds a quotient P sub G, which is going to be a P group of nilpotents class less than or equal to M sub G, in which this G survives. And then one looks at the map G into the product of the P sub G's. This group here is nilpotent because we had a bound on the step of nilpotence of each of the factors. The image is finitely generated because G is finitely generated. And since G is non-trivial in each of the factors, G is not in the torsion subgroup of the image, And so in particular, G survives in a torsion-free nilpotent quotient. So that's how the two are related. So now, as far as this table goes, let me state some precise theorems which will explain why they work the way they do. The first theorem is concerning the first interesting case, which is Solv geometry. So every manifold admitting Solv geometry is virtually a torus bundle with hyperbolic monodromy. So let A be an element of SL2Z, which is hyperbolic. And we let G sub A be the pi 1 of the associated torus bundle. Then G sub A is residually P if and only if P divides the determinant of A minus the identity. And so from this theorem, one can see that Solv geometry is never virtually residually torsion-free nilpotent because we can never arrange every prime to divide the determinant, or we are actually using that 1 implies 2 here. But it's not immediately obvious why every prime eventually divides powers of a, let's say the determinant of a to the n minus I. But that it is true that there is some n so that a particular prime divides the determinant of a to the n minus I. That follows from the next theorem, which is a generalization of this theorem for fibered 3 manifolds. So if C is a mapping class, which is to say a homeomorphism up to isotopy, and we assume that C acts unipotently on the homology of sigma with Z mod PZ coefficients, then the fundamental group of the associated surface bundle, G sub C, is residually P. And so this in particular shows that if you have any fibered 3 manifold, when that fibers over the circle, then there is a finite cover whose fundamental group is residually P.
You said a corollary to this theorem?
Yes.
Maybe if you can write it a bit.
Yeah, sure, absolutely. So a corollary is if M fibers over the circle, then there exists a finite cover such that pi 1 of M prime is residually P. Is it clear why this follows? So we have.
Oh, because on a cover, the action becomes important?
Oh, I mean, in fact, we can assume that the action is trivial on a cover, because the automorphism group of the homology with Z mod P coefficients is finite.
Okay, okay. Yeah. So what happens then in the first theorem if you start with this A, this mapping tools of this hyperbolic?
Yeah.
But if you pass per cover, then it becomes residually P, although.
Yes. So so a corollary in particular is that if you fix A and you start taking powers, then eventually every prime will divide the determinant of A to the n minus I.
So these Solv bundles are not residually P, but
Virtually residually P. And there's only one Solv bundle, really, which is not residually P for any prime. And that's precisely when, so I'll write it as a proposition. G sub A, SL2Z, is not residually P for any prime if and only if A is conjugate over Q to 2, 1, 1, 1. And this is, at least one direction is easy to see. If we write the fundamental group G sub A is generated by a stable letter T and Z2, then the conjugation action of T on Z2 is given by applying A. So in particular, forming the commutator T with Z2, like this, forming this group. This is all of Z2. And so in particular, this is because A minus I is an element of GL2Z. And so in particular, the lower central series of this group G sub A terminates after one step, and we can never hope.
Because in other words, G is a node group, right? It's a figure 8 node group, so that's happens for any node group. Let's say fiber node group.
Is that so?
Yeah. Also, let's say I should finish immediately. I mean, this will use A minus A in GL2Z, which
Yeah.
would happen for not automorphism.
Okay.
On the one sequence.
Yes. Okay. And so.
So that's one direction, right? That's about the other direction.
So.
Is that the only one?
This shows that if A is conjugate to 2, 1, 1, 1 over Q, then you cannot then you're not going to be residually P for any prime. On the other hand, if we can write any hyperbolic element, so if we have a hyperbolic element whose trace is n, then we can write it as n minus 1, 1, n minus 2, 1, and this is its conjugate to this over Q. And so in particular, we look at this, and so A minus I is going to be n minus 2, 1, n minus 2, 0. And if we square this, this is 0 modulo n minus 2. And so in particular, A minus I is nilpotent modulo any prime, which divides n minus 2. And now what's special about 2, 1, 1, 1 is that it's the unique Q conjugacy class inside of SL2Z where n minus 2 is equal to 1. And so that's the other direction. So now, to understand what's going on with PSL2R tilde geometry, there's the theorem is that if gamma is a discrete co-compact subgroup of PSL2R tilde, then gamma injects into a product which is the fundamental group of a surface cross n, where n is torsion-free nilpotent. And since the fundamental group of any surface is residually torsion-free nilpotent, which follows from the work of Maltsev, it follows that gamma is residually torsion-free nilpotent. And because n is a torsion-free nilpotent group, it follows that, in particular, that gamma is linear, which was, I believe, known, but there weren't many simple proofs known. And finally, so I now mentioned this work of Wise, which explains what's going on in the case of a hyperbolic three manifold. So let me just state that precisely and gather a consequence. So we start with gamma, a lattice inside of PSL2C. So this admits a faithful representation into SL2C. This is first attributed to Thurston, I believe. And so since this is a lattice, we in particular have that gamma is finitely generated. And so gamma admits a faithful representation into SL2 of K, where K is a number field. And so now K has a ring of integers O, and it's possible that gamma will sit inside of SL2O. And so if gamma sits inside of SL2O, or a conjugate of this inside of SL2K, this implies that gamma is virtually residually P for any prime. This is just, the proof of that is essentially the same proof which shows that SL2Z is residually P, virtually residually P. And if we don't have that, the image landing inside of SL2O, then outside of finitely many primes, gamma embeds into SL2O completed at the prime P so this is for all the finitely many primes. And then at these bad primes, the ones where we don't get an injection, we get a map into SL2 KP, where KP is going to be the fraction field of OP. And so now, when we get a representation like this, which is not conjugate to something sitting inside of the ring with discrete valuation less than or equal to 1, we get a natural action on the Brouwer-Tietz building, also known as the lattice tree. So in particular, we see that gamma acts non-trivially. On a tree. And this implies that gamma splits non-trivially as a graph of groups. And the theorem of Epstein, Stallings, and Waldhausen this implies that M is Haken. And so when we consider the fundamental groups of hyperbolic three manifolds, we either have we have a dichotomy. Either they embed in some arithmetic into SL2 over some ring of integers inside of a number field, or the manifold was Haken to start out with.
So when you say space is a non-trivial free product with amalgamation?
Yeah, it's a graph of groups. Yeah.
And so the theorem actually, so the splitting is reflected by the splitting of the three manifold?
Mm-hmm.
Like the JSJ splitting or what?
It's not a JSJ splitting because there are no incompressible tori sitting inside of the hyperbolic three manifold.
Oh, you started with this and I lost track of it.
Yeah, I'm sorry. So I
One is this three manifold group, hyperbolic manifold group?
Yeah.
Okay, all right, so this is speaking on higher genus surfaces then?
Yes. So they're all higher genus surfaces, and we can reconstruct the fundamental group of M as an iterated sequence of amalgamated products and H and N extensions over surface groups. And so the theorem of Wise implies that any Haken hyperbolic three manifold is virtually fibered. And so the theorem which I erased already implies that either we get the arithmetic case, in which case we're virtually residually P at every prime, or we're virtually fibered, in which case we're virtually residually P at every prime. And that's a justification for what goes on here.
So does it also show that we have virtually positive first Bethe number?
It does not, unfortunately, because we don't really have any control over how what the index of virtuality is. So for every prime, there's a different index which you have to look at to get residually P. It's possible that there is just one, or some universal one which holds for every prime, and that would be fantastic, and that would give you a positive first Bethe number. And so now, in the remaining time, I'd like to give some more of the details about the fibered case and why one would believe that you get virtually residually P in the fibered case. So there are two main tools. And the first is the Frattini subgroup. For a finitely generated group, G, we can define the Frattini subgroup, phi of G, which is equal to the intersection of all maximal subgroups. So this is a proper characteristic subgroup of G. So a well-known result is that when G is a P group, then G modulo its Frattini subgroup is isomorphic to H1 of G, coefficients in Z mod PZ. So in other words, the largest elementary abelian quotient of G. And the most important property of this quotient, which we need, is that if alpha is an automorphism of G, this is still assuming that G is a P group, and alpha is trivial modulo phi of G, then it follows that alpha has P power order.
So what is G? G is a P group now, right?
Yes. So in the case of a P group, if you quotient out by the Frattini subgroup,
Yes.
and you have an automorphism which induces the identity, then it has P power order. So that this fact, I believe, was known to Burnside. So it's a very old theorem.
Sounds like an exercise, a homework exercise in graduate course.
So I don't know of an easy proof of this, but it's not terribly difficult. So the other observation is something about the structure of the fundamental groups of fibered 3 manifolds. So when we have a fibered 3 manifold M, we have a fibration which looks like this. And so we can write pi 1 of M as a semi-direct product of Z with the fundamental group of the surface. And now the fundamental group of the surface is residually P. And so so we can find a lot of P group quotients of pi 1 of sigma. And now if we have any semi-direct product of 2 finite groups, so if we have the semi-direct product H, and we have that G is a Q group, and H is a P group, then G, and so this is a non-trivial semi-direct product, then G semi-direct product H is nilpotent if and only if P is equal to Q. And from here, it's not a difficult jump to see why, if we act trivially on the homology modulo P of the surface, then the fundamental group of M is going to be residually P. And to see that, we just assume that, so we see that if we have P, a P group quotient of pi 1 of sigma, then P mod phi sub P is going to be so we have a map from P, so this is going to be P ab tensor Z mod P, and the assumption that the monodromy acts trivially on the homology of the surface mod P allows us to choose P appropriately to identify this with H1 of sigma with coefficients in Z mod P. And then we apply Burnside's theorem to conclude that in fact, the semi-direct product of P with some cyclic group, which is just the image of the action of the automorphism, is going to be a P group. And that allows us to find a non-trivial P group where every element of a sequence of P groups where every element of the fundamental group of M eventually survives.
Maybe you have to say something. Like take sigma to be the torus, right? And take P to be just zima P.
Mm-hmm.
So I get zima P tensor zima P, which is zima P is H1 of the torus is zima P, but that's zima P squared. So are you seeing something?
Yeah, I mean
on that board, right?
yeah, sure.
Yeah.
So yeah, if sigma is S1 cross S1, then and we could take
So take P to be zima P, right? Because Z squared goes to zima P.
Yeah.
Right?
yeah, sure. I mean, yeah.
So you get no, just zima P. Go further.
So yeah, so you're making a very good point, which is why I said I didn't write it on the board. We have to choose P carefully. So we choose it. We have to choose it so that it actually factors, so that it actually admits a surjection onto this, which is that otherwise it's very bad things could happen. One has to be
Like.
yeah
Okay. All right.
yeah. You make a very good point. Okay, so I think in the remaining time I'll justify the comments I made about this about PSL2 R tilde. So what we have is we have gamma sitting inside of PSL2 R tilde. This is going to be a discrete co-compact. So we can assume that gamma is virtually pi 1 of some E where E is a circle bundle over a closed surface. We can assume that this is a non-trivial bundle. And because the monodromy group is finite, we can assume that E has trivial monodromy. And so it follows that the fundamental group of E is going to sit inside is going to fit inside of a central extension. Z maps to gamma maps to pi 1 of sigma, like this.
So you say trivial monodromy in homology, you mean? E is not trivial, but has trivial monodromy?
Yeah, it has trivial monodromy, but it's the Euler class is non-trivial, which that's the non-triviality of the bundle.
Okay.
So I mean,
it's something like a Heisenberg manifold or something, right? Like an important, like S1 bundle over S1.
yeah. So in particular, gamma is classified up to isomorphism by its Euler class E, which sits inside of H2 of sigma with Z coefficients. And we want to know, let's say we have this general setup, we have this central extension, and we want to find quotients of gamma. Suppose that we're given a quotient Q of pi 1 of sigma, and we want to know if there exists a quotient map from gamma to n, which makes this diagram commute. And the answer to this is completely homological.
So you require n to be what? Important or what?
No, so this is a general setup. So we will require it to be nilpotent later, But I'm just saying in a general setup, if we have some quotient of the fundamental group, we want to know if this extends to a quotient which makes this diagram commute.
Okay.
And so the general statement like this has, all we can really say is that n exists if and only if E is in the pullback of the cohomology of Q. Because we just pull back the cohomology along this quotient map and get that. So now, the first guess of what Q we should consider is z to the 2g. And the reason that's a natural guess is because we have the kernel C from pi 1 of sigma to z to the 2g, where g is the genus of sigma. The commutator subgroup here is going to be a free group. And on the other hand, this also gives us an infinite cover of sigma, and the bundle pulls back to it. But now that bundle is going to be trivial because free groups have cohomological dimension 1. And so the central extension is classified by 0. And so that's why z to the 2g is a good guess. And now we have a natural model for something which has fundamental group z to the 2g, and it's namely a torus of complex dimension g. And if we suppose sigma is a Riemann surface, which we can certainly do, then sigma has a Jacobian together with this natural map to it, the Abel-Jacobi map, which is injective, and it's an isomorphism on cohomology. And the map going the other way is a surjection on H2. And so in particular, we can construct the following quotient. We have z mapping to gamma mapping to pi 1 of sigma, z to the 2g, z like that, and like this, and there exists a quotient map which makes this diagram commute. And now every element g in gamma can be written as gamma dot z, where z is an element of the center, and gamma projects non-trivially to pi 1 of sigma. And so in particular, we have this natural map from gamma to pi 1 of sigma cross n, which we've just argued is an injection. And I think this would be a good place to stop, so I can take some questions.
Oh, well, thank you. That was a quick stop. I was barely ready.
Are there questions? Alex?
So what does this prove? This prove this the case PSL to R tilde?
Yes.
So can you maybe summarize it again? Maybe.
So if we have a discrete co-compact subgroup of PSL2R tilde.
Which basically corresponds to the circle bundle over a surface.
Yes. A non-trivial circle bundle over a closed surface, then we get a faithful homomorphism to a product of a surface group and a torsion-free nilpotent group.
Right.
This is residually torsion-free nilpotent.
Right.
And so this group in particular is residually torsion-free nilpotent.
Okay.
These are both linear groups, so this is also linear as a corollary.
So which one is the hardest case, hyperbolic case?
Yeah, so the hyperbolic case saying anything about residually torsion-free nilpotent hyperbolic groups is difficult as far as I can tell. I can make one remark in that if psi is a mapping class which acts unipotently on the homology of sigma with z coefficients, then the fundamental group of the associated bundle G sub C is residually torsion-free nilpotent. And the reason this is true is it uses essentially all the ideas that go into showing that if you have an element of an automorphism of a P group which induces the identity on P modulo the Fertini subgroup, then you get something of P order. This essentially it's an analogous statement.
So if your manifold does not have any so all three manifolds are virtually P then?
For every prime, every geometric manifold is virtually residually P.
But all of them are geometric.
Well, I mean, that's not quite true, right? If you have incompressible tori, then you may not have, they may not be geometric. And if it's not, if it's reducible, then it's not geometric. So if I had a hyperbolic manifold which has two of these torus cusps, for instance, and I glued these two together, then
So does the theorem fail then?
well, I believe it's true, and I still need to finish writing details. But
Theorems don't fail, Alex.
only we fail. Yes. If you glue these together, you get some sort of H and N extension, and their residual properties are much more difficult to deal with. And if this was hyperbolic, then gluing these two ends together, you don't get something that's hyperbolic anymore. You get something which doesn't have any geometric structure.
So before the talk, you were asking me about the Albanese and H2. What was it you wanted, and what would it give you if you had it?
I
Suggested you ask Alex.
I was wondering about if we were to replace pi1 of sigma by a general Taylor group, what sorts of things can you say about the unit tangent bundles of Taylor manifolds, for instance?
And I have one more question. It's kind of more for Alex. So I'm kind of under the impression I know a lot of your work, and I'm wondering what this relates to that I know about. Like, does this have some good relation to hyperplane arrangements that I don't?
Kind of morally, but not
morally. Yeah. Okay. So, is this stuff you've been working on recently?
Not really, but not too far away.
Oh, I was trying to see how it's related to work of yours that I'm familiar with, and it wasn't clicking with me.
So how much of this is written down?
So everything that I've said today is written down. I can. It's on the archive. The most recent version, which corrected a lot of the silly typos that found their way in is not on the archive. But I can, if you're interested, I can forward it to you.
Which part of the archives? Not algebraic geometry, presumably.
No. It would be under geometric topology.
Okay. Are there any other questions before? All right. Well, let's thank the speaker again. And